This video is an introduction to integration, which is a fairly major concept in the whole school of calculus, sort of mathematics. So we're going to start by looking at what exactly is integration, and I'll just give you a bit of a run through of how we go about finding it, and then we'll get into more of the detail as we go along through this chapter. So integration has many applications, but one of the most basic is to find the area under a curve. So when we're talking about the area under a curve, what we mean is the area between the curve, whether it's a straight line or a polynomial, whatever it is, but the area between that curve, between that graph and the x-axis. So if you've got a linear curve or a linear graph, it's pretty easy to find the area under that because this is just a regular trapezium. So we can use geometry to find the area of that, and that's really straightforward. However, when we get to something like this, it gets a whole lot more complicated. So there's a number of techniques we can use in order to make estimations on the area of this under the curve, and that's what we're going to be talking about for this video. So how we go about estimating the area is by using a series of rectangles or columns. Okay, so that's the curve I had on the previous slide. We want to find this purple area under here. But what we can do is break it into columns. So you can see these columns here. We can break those up. If we found the area of each of those columns, that would give us an estimation. Now, clearly for columns this size, there's some fairly major error. This one's much, much bigger than this area, and this one here is much, much smaller. These are a little bit closer. It will even out a little bit on a curve like this, but there will obviously be some inaccuracy there. If we make these rectangles thinner, so if you imagine we made this rectangle much thinner, we brought it all the way over here, and then the next one would start and would come down here. Okay, that would make the estimate a lot more accurate. So what we need to try and look at is how can we make those rectangles as thin as possible without actually reducing them to zero, because that doesn't make any sense, in order to get our estimate of the area as accurate as possible. So there are a couple of ways we can do this. The first one is called the left point estimate, and then you will see that we will do a right endpoint estimate. Okay, so we've got this example here. We've got a curve which is a quadratic, so 98.1x squared, and we want to find the area under that curve between x equals 2 and x equals 5. So in order to do this, what we've done here for a left endpoint estimate is we've split it into 6. Now this is sort of just arbitrary. You could have made 10 or 20, but for simplicity's sake, this one we've just chosen 6. Okay, and we divide it into those 6 columns. They're all of width 0.5, so you can see that width there, that's 0.5. Okay, and the top left corner of each column lies on the curve, so that point lies on the curve, which means there's a little bit of excess area here, and then this point lies on the curve, so a little bit of excess there, and so on. Okay, so in order to find the area of each rectangle, we need to do the width times the height. Okay, so if we look at R1, well, we know the width is 0.5 because we set it as 0.5, so that's our width. Okay, and then we want to times the height. Now the height of this rectangle is going to be the f of the value of the function when f is 2. So when x is 2. Okay, so when x is 2, what is the value of this function? So we're looking at f when x is 2. So that's width times height. And if you work that out, because you can plug 2 back in here, what you would get is 5 times 8.6. Okay, and then you get 4.3. So that's the area of that rectangle R1. Now we can do the same for R2. And what you get is 0.5 times f, and now we're doing when x is 2.5, because we've now come across to here. This is when x is 2.5. What is the value of that function? And that will be, if you work that out, that's 8.38, which will give you a total area of 4.19. And then you can carry on and you find that R3 is 0.5 times 8.1, which gives you 4.05, etc., etc. And if you add them all up, so you sum them all together, what you will get is a total area of 23.62 units squared. Now you can see that that's going to be a bit of an overestimate, okay, because we've got these little extra areas, all these little bits up here. It's not a lot, but it's a little bit, and so it's going to be a bit of an overestimate because the function, this particular function, is decreasing over that interval. so it'll be a bit of an overestimate. But what we can say, if we're going to generalize this, we can look at a function where we're looking between a and b, and if we denote a as x naught and b as xn, so we've basically divided it into, oops, I'm going blue. We've divided it into n intervals, so n columns. Then the width of each column is going to be just the distance between, so it'll be b minus a, and then divided by the number of columns. Okay, so that's the width of each column, and the height of each column will just be the function, the value of the function at that point. So it'll be f of x naught for the first one, then f of x1, and then f of x2, etc. Okay, and we start with f of x naught because of course we're doing left point estimate, so we're doing this. So the left point of each column is on the curve. Okay, so if you actually write that out, we say that the value of the area under the curve using the left endpoint estimate is going to be b minus a over n, because that's your width, times the function, sum of the function values. So fx naught, so it's the width times fx naught plus the width times f of x1, etc. And that goes all the way up to f of xn minus 1. So it's the 1 before n. This one in here is xn minus 1, and that's our last height there. Okay, so that's for your left endpoint estimate. Now we can do exactly the same thing with the right endpoint estimate, except instead of having the point on the curve up here, we take the right one. So it's this one, this one, this one, and you can see that we're going to get a bit of an underestimate here because each of those columns is a little bit smaller. So doing exactly the same thing, R1 it's going to be 0.5. Instead of being the value of the function when x is 2, it's going to be the value of the function when x is 2.5, because we're looking at the right point here. Okay, so we already worked that out as 4.19, and then we had R2, which is going to be 4.05, and then R3, we can work out, and so on and so forth. Okay, and you end up with your sum, and that will give you 22.67 units squared. Okay, and that's a little bit of an underestimate. Because each of those columns is a little bit shorter than it needs to be, so you kind of miss this bit here and this bit here and so on. And as I said before, the narrower you made those rectangles, then the closer it would be to the actual area. Of course, the narrower you make it, the more calculation you have to do if you're doing it sort of longhand like this, where you're calculating each one at a time. Now, again, we can generalize and say, well, we're doing the right endpoint. Okay, so we talk about Rn. It's the same, b minus a over n. That's your width of each column, except this time we're doing this. So again, this one here, and this one here. Okay, so the first function value we need is not x naught, but x1. F of x1 plus f of x2, etc. And of course the last one will be, in this case, f of xn. That one there. So very similar to the right, just kind of bump the whole thing sideways, one value of x. Okay, so that's our right endpoint estimate there. Now, let's get straight into a couple of examples, and then we'll talk a little bit more about how we sort of formally define this with limits. So we've got a question here which is out of the textbook exercise, and it says we want to approximate the area of the shaded region. We've been given the intervals, and we want to use left endpoint, and then right endpoint. So for left endpoint, that's where we do this one. So it's going to look like that, and then here, and so on. Okay, so because the width of each of these is 1, we're just summing. So the area, so for left, is going to be 1 times the height of the function at that point, which is just 5, plus, and then it's 1 times the height of the function at this point, which is 3.5, and so on, then plus 2.5, and then plus 2.2. It's 2.2, and that will give you 13.2 units squared. Okay, and if we're doing the right endpoint, then we'll have looking like this. So right endpoint means we're coming in here instead. And there, and there, and there. Okay, so you can see there's a big difference in between those ones. And what you'll get for that one is we start at 3.5. So 3.5 plus 2.5 plus 2.2 plus the last one there is 2. And that will give you a total of 10.2 units squared. Okay, so that's the difference between the left endpoint and the right endpoint. So in this case, probably because the width of these columns is quite large, the difference there in the estimates is quite significant. Now I'm just going to pause here because we do have a couple more examples to go through, and I don't want to make each video too long, so I'll just pause here and we'll pick it up in part 2.